Hello friends, welcome you all to the 7th lecture on function analysis and its applications. In this lecture, we will discuss the convergence Cauchy sequence in normal linear spaces and Banach spaces with examples. These are the contents of today's lecture. Convergence in normal linear spaces, Cauchy sequence, complete nonlinear spaces, Banach spaces with examples. First, convergence in nonlinear space. Let X be nonlinear space. A sequence Xn is the element of X is said to converge to an element X0 belongs to X. If epsilon greater than 0, there exists a positive integer n0 such that norm xn minus x0 less than epsilon for all n greater or equal to n0. Meaning of this, if xn converges to the point x0 belonging to x, then we can write limit n tend to infinity xn equal to x0, where x0 and xn both the elements of x. In other words, we can say that xn tend to x0 as n tend to infinity. Theorem. In a nonlinear space, a convergent sequence has unique limit. Proof. Let X be nonlinear space and let a sequence Xn belonging to X has not unique limit. Okay. By contradiction, we will prove the nonlinear space convergent sequence has unique limit. Okay. Suppose here Xn belongs to X has not unique limit. Suppose it has two limits X and Y. So as per definition, if Xn converges to the point x0, then norm Xn minus x0 less than epsilon, that is tend to 0. So here norm Xn minus x tend to 0 and norm xn minus y tend to 0 because it has two limits x and y as n tend to infinity. Now from the triangular inequality of the norm, we get norm x minus y equal to norm x minus xn plus xn. We have added xn and subtracted xn. Applying the triangle property of norm, this is less or equal to norm of xn minus x plus norm xn minus y. But norm xn minus x tend to 0 and also norm xn minus y tend to 0. It means both terms tend to 0. It means total sum tend to 0. It means norm of x minus y tend to 0 as n tend to infinity. So second property of norm, that is norm x equal to 0 if and only if x is equal to 0. Applying this property, here norm x minus y tend to 0. It means norm x minus y equal to 0 if and only if x minus y is equal to 0, that is x is equal to y. So here it is a contradiction. Sequence xn belongs to x has two limits, x and y. Here x is equal to y. This shows that xn has unique limit. Next definition, Cauchy sequence in non-linear space. Let X be a normal linear space. A sequence Xn belongs to X is said to be a Cauchy sequence if for every epsilon greater than 0 there exists a positive integer n0. n0 depends on epsilon such that norm xn minus xm less than epsilon for all nm greater or equal to n0. This means that if xn is a Cauchy sequence in X, then norm xn minus xm tend to 0 as m n tend to infinity. Theorem. In a non-linear space, every convergent sequence is a Cauchy sequence. But converse is not true in general. Let us prove. Let X be non-linear space and let Xn is the element of X converges to the point x0. Then for every epsilon greater than 0, there exists an integer n0 such that norm xn minus x0 less than epsilon by 2 for all n greater or equal to n0 as per the definition of convergent sequence. Okay. Hence, for all mn greater or equal to n0, we can write norm xn minus xm is equal to, here we have added x0 and subtracted x0. Okay. So norm xn minus xm equal to norm xn minus x0 plus x0 minus xm. Applying the triangle inequality of norm, that is less or equal to norm xn minus x0 plus norm x0 minus xm. So as per this condition, because xn is a convergent sequence, so norm xn minus x0 less than epsilon by 2. Okay, this is also less than epsilon by 2. That is total quantity less than epsilon by 2 plus epsilon by 2, that is epsilon. Hence, norm xn minus xm less than epsilon for all mn greater or equal to n0. Okay. What is this? This is the Cauchy sequence of nonlinear space as per the definition. So we can say that every convergent sequence is a Cauchy sequence in nonlinear space. Noting point, the converse of the above theorem is not necessarily true. For example, let X equal to semi open interval of 0 and 1 as subspace of R with norm defined this equal to mod. If any point of X, then norm of the point is equal to mod of the point. Then X is a nonlinear space, already proved in previous lecture with this example, is a nonlinear space. Okay. So let X is equal to semi open interval of 0 and 1 and let a sequence 1 by n as a Cauchy sequence. If xn is equal to 1 by n and xm is equal to 1 by m, then norm 1 upon n minus 1 upon m less or equal to 1 by n plus 1 by m. As mn tend to infinity, this tend to 0, which shows that 1 by n is a Cauchy sequence in X. But sequence 1 by n and limit n tend to infinity 1 by n tend to 0. Okay, but 0 is not the element of X, this interval 0 and 1. Hence 1 by n is not a convergent sequence in X. So every Cauchy sequence is a convergent sequence is not true. Proposition: let X be a non-linear space over the field K. Let Xn and X are the element of X with limit n tend to infinity Xn is equal to X, then Xn is bounded. Okay. Proof: since Xn tend to X as n tend to infinity, as per definition, we can write this norm Xn minus X tend to 0. There exists positive real number m such that norm Xn minus X less or equal to m. Okay, because this is tend to 0, it means this is bounded. Okay, for all n, so that norm Xn can be written as norm of Xn minus X plus X. Here we have added X and subtracted X. That is no change in norm Xn. Okay, but after applying the triangle inequality of norm, we can write this less or equal to norm of Xn minus X plus norm X. So here norm Xn minus X less or equal to m, and this is also a norm X. X is the element of X and norm X is a scalar. So both terms less than infinity, that is bounded. Okay, so norm Xn is bounded. Next theorem: if X is a non-linear space, then norm such that x to r is a continuous function on X. Norm is a continuous function on X. To prove that the norm is a continuous function on X, it is enough to show that if Xn converges to the point X as n tend to infinity, this implies that norm Xn converges to the point norm X. Here Xn converges to the point X, then we can write norm Xn minus X less than epsilon for all n greater or equal to n0. Okay, then we have to prove norm Xn tend to norm X. Okay, meaning of this is this one. Now we know that mod of norm Xn minus norm X less or equal to norm Xn minus X less than epsilon. Okay, why? Already in previous lecture we have proved mod norm of X minus norm of Y less or equal to norm of X minus Y. Okay, using this property we can write mod of norm Xn minus norm X less or equal to norm Xn minus X, and here given Xn converges to the point X, that is tend to 0. So here norm Xn minus X less than epsilon for all n greater or equal to n0. Therefore, this quantity less than epsilon, that is mod of norm xn minus norm x less than epsilon. Meaning of this quantity tend to 0 as n tend to infinity. That is norm xn tend to norm x as xn tend to x as n tend to infinity. This proves that the norm is a continuous function on x. Here norm as a function of xn converges to the function of x as xn tend to x. So this proves that the norm is a continuous function on x. Next theorem. Let X be a non-linear space and F be a field, that is RRC, set of real number or complex number. Then the mapping F such that X cross X to X. That is, if X is the element of X and Y is the element of X, then Fxy x plus y, x plus y also the element of x, and G such that f cross x to x, that is G alpha x function G of alpha and x equal to alpha x, then both function f and g are continuous. In other words, vector addition this and scalar multiplication this are jointly continuous. Proof. Here X and F are regarded as metric spaces because X is nonlinear space with matrix norm x minus y and mod alpha minus beta respectively. Okay, here is x and y are the elements of x and alpha beta are the elements of f. Okay, let xn, yn, x, y belonging to x and alpha n and alpha are the elements of f such that xn converges to the point x, yn converges to the point y in x, and alpha n converges to the point alpha in f. Then we can write norm xn minus x tend to 0 and norm yn minus y tend to 0 and mod alpha n minus alpha tend to 0 as n tend to infinity. Okay, as per the convergence sequence in x and alpha. Now f of xn yn minus f xy equal to value of f of xn yn is xn plus yn minus x plus y. Okay, because here f xy defined x plus y, so f xn yn can be written as xn plus yn and f xy can be written as x plus y. So this and this can be written as xn minus x and yn and y can be written together as yn minus y by using the triangle inequality of norm. This is less or equal to norm xn minus x plus norm yn minus y tend to 0. Why tend to 0? Because here norm xn minus x tend to 0 and yn minus y tend to 0. Okay. So, total quantity tend to 0 as n tend to infinity. So, as per the definition of the convergent sequence in norm, we can say that f of xn yn converges to the point of f xy as n tend to infinity. Again, second function g alpha x equal to alpha into x, and also we have to prove g alpha n xn tend to g alpha x. So, norm g alpha n xn minus g alpha x can be written as norm of alpha n xn minus alpha x as per the value of g alpha n xn and the value of g alpha x. This term can be written as alpha n xn minus alpha n x plus alpha n x. We have added alpha n x and subtracted alpha n x minus alpha x. This one. Okay. Again, applying the triangle inequality, then norm of alpha n xn minus alpha n x plus norm of alpha n x minus alpha x. Again, applying the third property of norm, that is norm alpha x equal to mod alpha norm x. Okay. So, this quantity less or equal to norm of alpha n xn minus alpha n x plus norm of alpha n x minus alpha x. Here alpha n common. So, applying this property, we can write mod alpha n norm xn minus x, and in this x common, so we can write this alpha n minus alpha into x. Okay. So, again applying this property, we can write mod alpha n minus alpha norm x. Okay. So, here given norm xn minus x tend to 0 and mod alpha n minus alpha tend to 0. So, this tend to 0 and this is also tend to 0 as n tend to infinity. So, total tend to 0. Hence, f and g are continuous. Next definition, completeness of Cauchy sequence. A nonlinear space X is said to be complete if every Cauchy sequence in X converges to an element of X. That is, norm xm minus xn tend to 0 as mn tend to infinity. That is a Cauchy sequence. Then there exists X is the element of X such that norm xn minus x tend to 0 as n tend to infinity. Okay. Any sequence xn converges to the point x, then we can say that the norm xn minus x converges to point 0 as n tend to infinity. That is complete. Banach space. A complete nonlinear space is called a Banach space. For example, the real linear space R and the complex linear space C are simplest Banach spaces with the norm this defined by norm x equal to mod x for all x belonging to R or C. Already we have discussed in previous lecture of this course that the both spaces R and C are nonlinear spaces under the above given norm this. Also we know that these spaces, set of real number and set of complex numbers, are complete, hence they are Banach spaces. In this lecture, we have discussed the convergence Cauchy sequence in nonlinear spaces, complete nonlinear spaces, and Banach spaces with their properties and some examples. These are the references which have been used in this lecture. Functional analysis, Dover publications, written by George Bachman and Lawrence Naresi. Introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Function analysis, New Age International Publisher, written by B.V. Lemieux. Function analysis, Tata McGraw-Hill, written by Waterrudin. Thank you for your attention.